and start recording again. And we'll have the video in 2 pieces this time, because I think I did indeed cause a problem with that. So I'll have to remember that. Okay, so let's see, that's the console thing. So let's go back to our blink.c. I can't do cd dash. Let's go, oh, it's in a separate terminal. There, escape. Okay, so I got this, looking at our consoles up here, and we got a way to break out of this thing. If not vc underscore const at position I, then we're gonna stop this. This is why it's not a loop that runs up to 63 necessarily. We just won't go any further than 63 under any circumstances. So vc const. Okay, it's mentioned a bunch of times here. Where does it come from? Okay, for vc cons, it's coming from linux/console struct.h. Okay. I think it's actually in this one. I don't think this one will be as long a rabbit trail. Okay, vc cons, extern struct vc. So that's where vc cons is coming from. And what vc cons is, so I was mentioning, let's use an array notation here. We're declaring an array. We've got to start parsing this. Let me give you an example to make this work. I'm not going to save this change. Suppose we said int r_array, and then we said something over here, max size. Okay, that one makes all the sense in the world, right? Because we're declaring an array, and it's max size integers. Okay, next iteration. Instead of integers, we're going to make an extern struct VCs. Okay, makes sense now? So instead of an integer here, the separator is right there. And so this point right here is the same as that point right there. So we'll go line it up here. And so we just got a different data type. Now I could take the extern out if it makes you happier. But that's what we're looking at there. Okay, meaning of the extern keyword. You're saying extern all over the place here. Extern something, extern something, extern something else. What this means is when you take the header file and you include it in a couple of different files, instead of declaring a separate one of these every time the header file is included, we just have one. And when you include this file, it's going to be an extern one, as in it's something that's also used in a different one. Let's look at it like this. Okay, so suppose you have include something, A. And then you've got 2 files over here, and you put this line in this one, and you put this line in this one. Well, include basically means cut and paste. Like take this header and stick it up here. And so if inside this file A here, you said something like int x, then you're going to have int x and x. Okay. And that's not quite the circumstance we want here, because then you have 2 things that are called integer x that are in different files. That's not what we want. And so when you say extern int x, you only get one thing called int x, and they end up sharing it. So that's what the extern construct here is for. Okay, this goes a long ways. Define stuff, if not def, whatever, def. Okay, that's fine. So this extern struct. So you might ask, well, why do we want it to be an extern struct? Okay, go over here. So we were going to make this module, right? And in this module, we're about to go use this thing called VC cons. Well, what we want to get out of VC cons is some information about each of the consoles. And if we go make a brand new thing called VC cons, we're going to have to go find that information somewhere else and put it in here. But that's not what it is. It's our mechanism for learning about our consoles. And so we're declaring that we're going to have an extern structure here, extern struct array called VC cons. And then when this file, when this here gets mashed into the kernel, we're going to get the VC con structure that was already defined in the kernel. So it's external to this file because the actual memory was allocated somewhere else and this thing was actually made somewhere else. But here in our file, we're able to use it. And this is going to be a real common pattern for how we get information out of the rest of the kernel and start using it. And it also kind of illustrates this whole thing. And I've been talking about this, this module getting mashed into the kernel and becoming part of it. Well, we're sharing variables with the kernel. And so, you know, this is you know, we're inside. We're part of it, you know. We can share its toothbrush now. You know, this is we're part of the kernel. Okay. So we're looking at this .d member of item I of this VC construct. If you look over here again, what's a VC? Well, it's got a VC data star D. And so this is a pointer to a struct VC data here. And a VC data, I think that's defined just up here. A VC data has quite a few members, actually. And it looks like they're mostly just characters and things. I don't see any function pointers in here. I do see some other structs and that kind of stuff. But mostly we're just looking at data. There's a few other structures incorporated in it. And we didn't go check to make sure none of those have a function pointer. But this looks like just a regular data struct. Okay. So this check here, if not VCCons at position I.d, we're checking to see if this pointer here, this pointer to another struct, happens to be 0. And if it is 0, then we're going to break and finish. So basically, we got this VCCons, this array of you know, 63 consoles, and the unused ones on here are going to have .d set to 0. And so that's how we're going to know to stop our loop. Okay, so there's a quick exit. And so then we're going to print out some stuff about the kernel here. I, that's you know, our loop counter, what we're on. Max in our consoles, as in the maximum number. And the VC underscore num. Okay, let's switch back to this. What's VC num? Okay, console number. And it's a short, so it's 16 bits. And yeah, there we go. So we got a 16-bit number. And so yeah, LX correct for that? Oh, LX is for that one. We're just using a percent sign I there. And so then here, this unsigned long VCCons port.tty. Okay, well we can figure out what that is too. Because we're looking at the data structure VCnum, so this is the data struct up here, and in port. And what port is a struct tty underscore port. And what's one of those? Okay, it's probably in bt.h. Okay. Oh, okay, maybe it's not. I'm going to grab tty port for everything in here. Okay, so we got a whole bunch of places where they're set and made and things. There's a tty port operator there, tty.h. Struct tty port. Okay, so they're declaring that there's going to be one, and here's what they are. Okay, so that's what a tty port is. I forgot what member by now we're after. So it's one of those .tty. Okay, where's tty? That's a back pointer to a tty struct. Okay. Well, you know, the rabbit hole keeps going here for a while. We're taking that pointer, turning it into an unsigned long, and we're going to print out what it is. And it'll be unique for each of the consoles on here. Okay, so after that, we finished scanning consoles. Okay, so then down here, we're looking for a driver. And we're looking inside this VG things at FG console. Okay, what's FG console? Well, it's mentioned in a couple of places. Oh, it's apparently defined in tty.h. Okay. So let's go take a look at, oh, this is tty.h. FG console. I said it was defined in tty.h. No fair. Well, it said for SG console. And that doesn't necessarily mean it's in here. As you can see, we've got some other files included. And it could be in any of those. Okay. There it is. It's in BT kern.h. Okay. It's an extern int, FG, okay. And that is where it is declared. And it is, in fact, not mentioned other than that here. But you notice where it's an extern int. So it can actually get changed by some other piece of code. Indeed it will. Okay. I think it actually stands for foreground console. And it's the console that we're actually using. And so we're looking down at for a port, a TTY, and driver. And that's going to give us a my driver. Okay, let's go see what exactly one of these things is. Oh, and where's my driver come from? Hey, it's actually declared right up here. A struct TTY driver. And that is what my driver is. Okay, what's one of those? TTY driver. Everywhere. Okay. TTY driver.h. Okay. So it's got a long explanation right up here, and the entire file a comment? Probably not. Okay. So it declares a struct TTY driver here, and that's because it's going to be included in this TTY operation struct. Oh, there it is. Okay. So now we finally get to what the magic was. The magic is an integer. Everything is simple once you distill it into its basic elements. Okay, so it's a magic number for this this structure, it's going to be a reference that's going to be of some use to us. And you got some other stuff: major device number, minor device number, number of devices allocated, type of TTY driver, etc., etc., etc. Okay. And so that's what one of those things is. Let's take a look up here real quick. And wait, the whole comment, and they don't actually give any insight into what TTY driver is at all. Well, that's fine. Okay, so we got this this my driver here, and this is a TTY driver struct, and then we're getting the magic number. So we can see the magic number here. The magic number is 5,402. Okay. Remember that. Put it on a test. What was the magic number? Just kidding. Okay, anyway, so we print that out. Okay, now down here, we got to get to the actual blinking stuff. And where's the actual blink function? The actual blink function is right here. And so we're calling this whole thing right there. That's actually duplicated from right down here. And this all happens after this whole timer thing. Let's skip the timer for the moment. We'll get back to it. I hope. This is setting up a timer that will make this happen periodically, basically. Okay, so we got this thing here, my driver ops IOCTL, and then we got this second thing in parentheses over here. So trying to distill this whole thing down to its essence. Let's take a look at what my driver ops IOCTL actually is. And so if we look at this my driver thing, where was my driver? Was it in here? Oh yeah, it was a struct TTY driver, right? Okay. Okay. And so if we go down all this stuff, okay, TTY driver. And inside here we had a member called ops. And so 10 extra credit points to the first one that sees it. There it is. Hey, I get 10 extra credit points. Okay, so we have this struct TTY operations ops. And so we're going to go take a look at that. And I think that's actually up here. What's that?
It was about this.
Yeah, right here. TTY ops. And so we're looking at IOCTL. Okay, let's look for a member called IOCTL. That's right there. And this is a function pointer. So you can see here, this is a function pointer to a function that's going to return an integer. The struct member is called IOCTL, and the function that it points to takes a struct tty, and an unsigned int command and an unsigned long arg. Now, it takes this tty struct. And so the tty struct, I mean, this dumps us into the whole rabbit hole, but at a fairly high level, because the tty struct, remember, had just about all the information about this, this driver in it. So that's kind of our equivalent of Python's, is it this or self in Python? I can't remember now. Self. That's like kind of the equivalent of the self pointer in Python. We're going to call the function that this whole thing points to, and as a parameter, we're going to give it, you know, a few references back, so it has all the information it needs to work with. And this does mean that we're giving it something such that if it followed the rabbit trail, it could get to its own memory address, which, you know, it doesn't need to do, but it does. So that's giving us kind of our equivalent of a self pointer there. And so we're looking at a function pointer here that takes these three parameters, a struct tty struct, and an unsigned int command, and an unsigned long arg. Okay, so here is our three parameters. The tty struct pointer, and that's you know there, and then this kd set led and all LEDs on. And so these are our two numbers there at the end, the unsigned int and the unsigned long. So, am I an unsigned long? Okay, so we got this all LEDs on. That's set to 0x7, and, excuse me, 007, which is the same thing as 0x7. Like, it would be the same number if we took out that 0. Oh, the other one was like something else. It wasn't one of those, was it? It was k set LED, which is defined in kd.h. Okay, we've had a lot of wild goose chases so far. Not wild goose chases. We've been successful. We always find what we're looking for, right? It's like my cat chasing a rabbit. I mean, eventually she'll find it and she'll bring it home and it will die under the dishwasher. I talked to my Linux class about that. Have good fun in that class too. Anyway, so
the rabbit died under your dishwasher?
Yeah, it did. Yeah, it was rotting under there, and my wife kept saying that there was some problem. Like every time she ran the dishwasher, she said it stunk. Like there was a rotten camel in the kitchen, and I couldn't smell it, so I thought she was nuts. And after about 3 or 4 weeks of I was like, I'm gonna pull it out and then like show her that there's nothing rotting under the dishwasher. So I pulled the dishwasher out, and there's like this dead rabbit rotting under there. It was all stuck to the floor.
My sister owned a very small cat that really liked to, she couldn't have cats at her apartment, so she was living with me and my dad. And she really enjoyed bringing in birds into the house and usually not actually killing them. So there was a few mornings where I woke up with a bird flying around my room, about 3 actually, and then I called her and told her to take her cat and take it somewhere else. But she did.
They like to do that.
Yeah, it was really annoying. I don't like to be woken up by flying things in my room.
Oh. Well, you just need another cat that actually kills them to keep it inside.
No, we had like 3 cats actually. The other 2 cats just looked terrified because they didn't know what she was doing, I guess. I don't know.
You can keep bringing home cats until you find one that actually gets the bird. Okay, so we're successful on our hunts usually, but I want to actually finish explaining this file today. So this kd set led is just a value that gets sent to this this console that tells it to set the LEDs of the keyboard that's associated with it to whatever value it's given. And now the value up there, 0x7. Anybody here remember Linux permissions? That's just nods. Yeah. That's all 3 LEDs on. I don't remember which one's which, like which one's scroll lock and which one's num lock and which one's caps lock. We could figure it out if we changed it to like 5 or something, and then we get 101, and but that's how it's set. And so we can manipulate that if we want to. Okay, so that's the function call there that goes into this whole thing, and this is part of what this whole project 1 is that I'm sure you're all working on by now. Figuring out how to parse all of the syntax like this and to deal with it and work with it. So this is a function call. That's all there is to it. Okay, so that line make sense now? Okay, that seems to be good, good. Okay, so this whole timer thing. We got this, we're initializing a timer. This init timer function, it's going to be coming in from one of the includes up here. I'm not sure which one, but one of them. Now this whole my timer, that is a struct timer list. And so we're making one of those. And then down here, we're going to be passing the address. You'll notice up here, we just made a struct timer list. Like we didn't go declare a pointer to a struct timer list and then call kmalloc, which is the kernel version of malloc, and go allocate some memory for it. We just went ahead and made one right here in our module. This is fine. You can do that. It'll give you some memory, so, stack memory, and your kernel module. As long as your kernel module is in the kernel, stuff you declare up here is going to stick around. And when your kernel module goes back out of the kernel, these will all go away, and you don't even have to do anything to make it happen. And so this is actually a pretty good way to declare a structure that you want to keep around. Now, notice this struct is defined global to this file here, global to this module. And so that way it's available in each of these functions. And that's going to be useful here. Okay, so we're going to initialize a timer, and we're giving it a pointer to that timer list. And so we're going to get a timer on that list, basically. We're giving it the memory address, so we can go ahead and change that list if it wants to. That's fine. We don't go look for the init timer function right now. But we're setting myTimer.function. So that's the function for our timer, and we set it to myTimerFunc. Well, here's myTimerFunc. And so this takes one parameter here, an unsigned long pointer, and you notice we're casting this as an int pointer. Why don't we use a void star here? I don't know. We don't use it. And it returns void. This probably has to match this parameter profile in order to be acceptable as a function for that. So actually, if we go and look up this myTimer.function, this is on a struct timer list. Okay. Okay, there's a whole bunch of places they're used. I kind of wanted when they're defined, struct timer list. Let's try this. Let's go for timer list, and then an anything, probably a space or a tab, and then an opening brace. Hey, there we go. Timer.h. Could guess that one, eh? Here's what a struct timer list is. And, oh, well, there's why we use an unsigned long. So we got this function. This is going to be a function pointer here. It's going to return nothing. It's going to be called function. You saw that before, because we used the dot function property, or a struct member. And it's going to take one parameter that's an unsigned long. So that's why we don't use a void star in the kernel module in blink.c. Why did the kernel designers use an unsigned long? Well, I don't know. I'm not one of them. Go ask Linus Torvalds. Lincoln can explain himself. Okay. So anyway, we got this myTimerFunc here that goes and gets stored in this function.
What are jiffies?
Jiffies. That's a unit of time.
Oh, okay.
It's fairly small.
Alrighty then.
So this KB LED status, we're giving a pointer to that. We're putting it on myTimer.data. Oh, and look at this. We're casting it on unsigned long. We might not have to ask Linus Torvalds here. We might figure this out in a minute. Okay, so we got this unsigned long data. And that, we're giving this KB LED status. Okay, up here we have this unsigned long pointer, and we're casting it to an int pointer, and then we're using it. In fact, it's a reference to something, isn't it? Like this character right here. Now, that's a little odd. This one's not Linus Torvalds' fault. This is something that's a quirk to blink.c. We're calling this a pointer to an integer, but it's actually a pointer to a character. And down here, we're casting the memory address of this character, KBLED status, as an unsigned long. And so then we're taking that memory address and storing it in data here. And so you can guess what happens at this point. Every time this function is called, it's given this parameter of data. And that's something for the function to keep around and change as it needs to. Question that occurs at this point, so why not just use the global variable KBLED status up here? Well, we don't necessarily, this function is going to get called at some other point. Like, it's going to get called by the timer routine. And the timer routine is not in this file. And so maybe that it actually can't access that global data, or maybe not. It seems like it should be able to. That's my speculation here. If we have time, we'll try accessing the global variable and see if it works. Replace speculation with knowledge. Be scientists. Study the computer, right? Okay. So we have that pointer there. And then this expires. So the timer is basically given a point where it's going to expire. Okay, jiffies. Okay, jiffies plus point delay. That's the 2 places it occurs. Let's define somewhere else. Okay, so I mentioned, yes, it's a unit of time, and that's the one we're on. So blink delay up here, hz divided by 5. That's giving it our delay. Okay. Jiffies, they're actually a variable unit. They're related to your CPU frequency, if I remember right. It's the frequency of something inside your computer. I think it's CPU frequency. It could be like front side bus frequency or something. I'm having trouble remembering exactly. But anyway, it's related to the frequency of something inside your computer, probably the CPU frequency. And so that's how it's being set. Now, you might ask, at this point, you can see some insight into why the frequency, why the blink delay might have been wandering. If we go cat proc CPU info, these ones use scaling on this computer. CPU megahertz 2400, that's maximum. 2400, 1200. So this CPU is ramped down a bit. This changes the rate at which jiffies occur. And so this is probably what we're looking at in terms of this inconsistent blinking. Instead of relating this blink interval to time, we related it to CPU frequency. This is a pretty old example. I had to change something or other on it to make it work on Linux kernel version 3. It was an example for 2.6. And so it's been around a little while. CPU frequency scaling is something that's been taken off, CPU frequency is something that's been around for like 15 years and really took off in earnest 10 years ago. So whether or not that's recent or not is up to you. But when I started using computers, we had a button on the, no. When I started using computers, we had CPUs that were pretty slow. And so people would write games like Pac-Man or whatever, where you play the game, and the delay was related to the CPU frequency. Then later, the second computer I used a fair bit, it was a 386, and you had a button on the front that would take it down from the blistering speed of 16 megahertz down to 8, so that your Pac-Man game would slow down and you could still win. Then after that, there was a long period where the frequency was static. Like you'd buy a CPU and it would be 400 megahertz, and that was how fast it was. But then after that, people started to like to carry the computers around in their backpack. I realize now people like to carry a computer around in their pocket, which is quite different. We didn't have that then either. But they started carrying it around in their backpack, and they like to have the battery last a long time, so the CPU frequency would ramp down when you weren't using it very much. Then eventually somebody got the bright idea, well, why not make that happen with a desktop computer, and then the fan doesn't have to work so hard and it doesn't use as much power. And that was about 10 years ago. And so now they pretty much all support that feature, including this one here. Oh, but back when this example was written for the 2.6 kernel, it was in that period when the CPU frequency was static. And so if you calculated your blink interval based on the frequency of the CPU, it would have actually blinked steady. Okay. Long explanation for not much good there. Sorry. Okay, so anyway, we set a point where it expires, and we call this add timer. This adds our timer to the active timers that the kernel has to manage. And then we turn all the lights on, and then we're done with the init function finally. Okay, so this my timer func up here. What this has to do is, it takes this p status here thing, and it either sets it to restore LEDs or all LEDs on. Well, restore LEDs is 0xFF, which seems to turn them off, actually. That would be my explanation of the procedure. Because you notice it doesn't really restore them per se, because if we had caps lock on and we start blinking it, then caps lock status goes away. So restore LEDs is maybe a funny name. And this might have actually changed since the example was written, the exact behavior. Maybe that example used to make sense. But my observation of the effect here is that sending 0xFF as your parameter to control the LEDs seems to turn them off. Okay, so if they're on, turn them off. Otherwise, turn them on. And so this P status thing here, yeah, you change this P status. And then you set them to whatever they were going to be set to. So if you wanted to turn them off, then here you actually do it. And we'll go ahead and add a blink delay. So this is the number of jiffies we're currently at. We add on a blink delay, and we add the timer. Okay, let's make a modification here. I haven't modified the source code the whole time. It seems so weird to me. What data type is expires? Expires is a unsigned long. We can print that with LD. Okay. Actually, we should go LU for an unsigned, because it was unsigned. Okay, and let's actually put some more explanation. Okay, and my timer. Okay, this is sort of a lousy idea because it's going to fill up the dmessage log with output, but that's fine. Okay. Oh. We are blinking. Oh, I don't have to use that to show you. I can just set that thing there and you can tell if it's blinking or not. Okay. And so there's our expires values. And you can see they are, increasing by, so much every blink. Jiffies are related to the CPU. They don't necessarily go one per cycle. It looks like our interval there is about 50, 47, 97, 47, 97 as they go on. Yeah. Oh, yeah. There we go. Stops blinking. Oh, I just realized that blinking is impossible to see on the video, and I've been waving the keyboard around. Sorry. Okay. So you got this timer. Okay, let's go back to blink. Make that see. And we're starting to run our time down here too. Okay. So that's the timer function. There you can see how that part works. The final function in this thing is this exit one, and all it does is delete the timer, stop the timer, and it calls this restore LEDs, which, judging from the name, I think the author expected it would restore them to their original state, but my observed effect now is it turns them off. So that's the end of it. And we should see that KB LEDs unloading if we go over here and go here and do message. There we go, unloading. Yeah, good. Okay, so that's that one. Now last time I said that I'd try to pull out some kind of module to make something go wrong with the computer. Yeah, sure, why not? We're about done with it. I won't pull a file system driver because that might hurt the video. Let's try a USB system. That might be a problem. You know what I'm going to do? I'm going to hit stop recording.